Yeah, so first, thanks for the invitation to participate in this really nice workshop. So I guess I don't really have to present much of a motivation because I guess you've heard by now enough talks already that hopefully convince you that being able to interface atoms and light in an efficient way is an exciting goal. So that opens up a lot of opportunities for applications like in quantum information processing, or to explore fundamental physics like many-body strongly interacting photonic states. And I guess a kind of a well-known issue is that in some sense, being able to create this kind of efficient interaction is intrinsically challenging. And you can understand that just from the basic building blocks of a single atom and a single photon. So for example, if you take a single resonant photon and focus it down to some area A onto some atom, you can actually calculate what the interaction or scattering probability is. And it's simply given by the resonant wavelength of the transition squared divided by the beam area. And the challenge lies in the fact that in free space, the light has to obey a diffraction limit. So if you literally try to build this experiment, you can get about kind of 10% interaction efficiency, which is quite high. But again, the challenge if you want to do a lot of these applications is to get as close to 100% as possible. So one kind of common approach to try and get closer to 100% is simply to use a lot of atoms instead of one. And then in that case, the interaction probability is enhanced by the number of atoms. And this kind of quantity here is known in kind of atomic physics language as the optical depth of your atomic ensemble. The importance of this optical depth, you can also understand from a kind of complementary viewpoint. So in particular, if I have a collection of atoms and I create just one excitation, but in some kind of collective fashion. So I have one excitation, but in a superposition of all the atoms. Then it's known that if I play with the phases of the excitations of each atom, then this system behaves a little bit like a phased array antenna. So it can efficiently emit into a preferred direction. So for example, like a Gaussian mode that I can efficiently collect into. And that emission is enhanced by the atom number. On the other hand, these atoms can still emit into 4 pi, and that continues to occur at the rate given by a single isolated atom, gamma naught. So the optical depth also has the meaning of serving as a branching ratio of information, and in particular, the probability that that the system emits a photon into the mode that you want, over the probability that it emits into 4 pi, the directions that you can't collect. And so once you kind of associate the optical depth with this kind of branching ratio of information, of quantum information, you can easily understand or believe that this optical depth then imposes fundamental limits on the errors of any application that you want to carry out. Just to give one example, one common application is a quantum memory. And the idea of a quantum memory is that you have some wave function encoded in photons. So it could be like a polarization qubit, for example. And you want to be able to store that or map it reversibly into some stable, long-lived atomic state for a long time. So there's a lot of different protocols you can implement to actually carry out this quantum memory. But there's this really kind of elegant theory paper from 2007 that says that no matter what specific protocol you try to implement, if you really optimize it, you're going to get the same identical maximum efficiency in the end, which only depends on the optical depth of the medium. And at least for kind of large optical depths, that error was derived to be 5.8 divided by the optical depth. So let me kind of show you what that looks like in a typical experiment. So this is from Julien Laurent's group from a few years ago. So what they're plotting here is the efficiency, or basically 1 minus the error, as a function of the optical depth of an ensemble. And what you see is that, as you increase the optical depth, the error does indeed shrink, but kind of not as fast of a rate as one would ideally like. And then, once you reach sufficiently high optical depths, actually the error starts to increase again. So in other words, when you accumulate too much optical depth, it doesn't really remain, the system doesn't really remain kind of fully functional. It creates other kind of technical problems. So this is just kind of one specific example, but I think it's pretty representative of what happens when you try to carry out a lot of other applications involving atoms and light. So one question you can ask is there some way that we can further improve the fidelities? And one thing that kind of caught my interest in the past few years is that in the kind of physics I described before, I said that if you have a collective excitation, then the kind of bad thing is that the atoms can emit that excitation independently into 4 pi. At a rate that's set by the single atom spontaneous emission rate. And it turns out that even though that's something that I learned and you learn in textbooks all the time, it's actually an assumption, and it actually neglects wave interference of light. To kind of understand that, if we take a step back, it's pretty well known in just kind of classical optics that if you have a collection of scatters that are randomly positioned in space, and then you send a beam of light through the medium, then what you get in the far field intensity pattern is a pretty complex speckle pattern. And that's due to all the kind of complicated multiple scattering and wave interference that can occur as light tries to propagate through this disordered medium. So when you see this kind of complex far field intensity pattern, essentially by conservation of energy, it can't really be that from the standpoint of atoms, the situation is so simple as the atoms are independently, spontaneously emitting. So somehow the emission actually has to be correlated to somehow match up with this kind of complicated intensity pattern. And so, it's a little provocative to say, but essentially what I'm saying is that, the textbook models we typically use for atomic ensembles don't actually include, the most basic optical phenomenon of wave interference. And it turns out that that kind of assumption, actually rises from just kind of historical attempts, a kind of natural attempt to try and create macroscopic models of light matter interactions. And so what I mean by that is, if formally you can write down the equation of the electric field, the wave equation for the electric field, which is coupled to the polarization density of your medium. Now, the polarization density, if we consider atoms, in principle should be a sum of delta functions, accounting for where the atoms are sitting particularly. But dealing with that kind of microscopic disorder is a little bit inconvenient. So what we tend to do, both in quantum and also just kind of classical electrodynamics, is to say that that kind of granularity can be smoothed out, and then my atoms can just be treated as a smooth density. But when you view this kind of picture here, it's clear that to get this kind of complicated speckle pattern, to get this interference, you really have to include the atomic granularity. So then one question one can ask is, if these kind of limits, if these error limits for applications are based on models that don't include wave interference, can we somehow build wave interference into our models and somehow exploit it to do protocols in a more robust fashion? And the general idea, or one possible idea that one can try to exploit is, if I try to now position the atoms in some ordered fashion to try and engineer the wave interference of the outgoing light, then what one might be able to do is, now if you create a collective excitation, you can not only get the same kind of collective enhancement into your preferred directions as before, but at the same time, you might be able to exploit destructive wave interference to kind of interfere away the bad emission into 4 pi. And if you do it correctly, that kind of emission rate into 4 pi might actually even scale itself with the atom number. So then the branching ratio of information can be actually kind of super linear in the number of atoms, because as you add more atoms, you can actually shut off the bad process. And if you can accomplish this, this branching ratio can then be much larger than your kind of conventional optical depth. So this is a kind of new concept that we call selective radiance. It's one of the kind of primary reasons that I'm quite interested in the optical properties of arrays these days. And I think it's also attracted interest from a kind of rapidly growing community. And that even starts from even a decade ago from pioneering work from Helmut Rich and Jana Rostakowski, for example. So that was a bit of an extended introduction. And in the rest of the talk, I'd like to focus on basically 4 things. So the first question is, how do you develop a kind of tractable quantum theory that includes multiple scattering of light in atom-light interactions? And then next, I'd like to kind of illustrate some consequences. So first, one kind of interesting consequence is that in the classical or single photon regime, if you can create a kind of 2D array of atoms, that system can actually function as a perfect mirror for resonant single photons. And moreover, I'll show how you can kind of utilize that effect to implement a quantum memory protocol that's selectively radiant, and which has a kind of error scaling that beats the conventional bounds. I'll then describe how you can kind of turn that mirror into some kind of nonlinear system in order to generate strong photon-photon interactions and implement a selectively radiant photon-photon gate. And then at the end, if I have time, I'll try to give some perspective on what this kind of multiple scattering, what kind of interesting phenomena can arise from the multiple scattering at the many-body limit. Okay, so in terms of trying to develop a formalism, let me just first explain the problem that we're generally interested in. So generally, we have some kind of collection of atoms whose positions can be specified. I send in input fields. I want to allow for the possibility of multiple scattering of light between atoms. And then what I'd like to do is I'd like to be able to calculate any kind of quantum correlation function of the outgoing field in space and time. And just to make the setup a little bit more specific, when I say atom, for the purpose of this talk, I'm mostly going to focus on a minimal 2-level model. So there's a single excited state, where if I just have a single isolated atom, it's going to emit a photon and drop back into the ground state at a rate gamma naught. And this transition has some resonant frequency, omega EG, and some associated resonant wavelength, lambda EG. So it turns out that part of this problem, at least formally, you can just easily write down a solution to. So basically, I can just kind of use a classical relation that holds in the quantum regime as well. I can always say that my total field at some position and time is the coherent sum of the field that I send in plus a field that's rescattered by my individual dipoles. And in the kind of quantum regime, the dipole moment of each atom is given by basically the atomic coherence operator, the atomic lowering operator. And that is multiplied by a so-called Green's function, which basically describes how a field propagates from the position of atom I out to my detection point. And so in free space, this kind of Green's function is nothing more than the kind of famous lobe radiation pattern of a point dipole. It, in particular, has the kind of well-known far fields lobe pattern, but also kind of 1 over r cubed electrostatic near fields. So basically, the main point to take away is that this equation says that I can formally derive all the correlation functions of my total field if I know the properties of the field that I send in, and I can calculate, and if I can calculate the correlations of my atoms. So then basically what one has to do is solve for the dynamics of the atoms. And so you can imagine that if I write down an equation of motion for the atoms will be driven by the light. But then according to my previous slide, the light can be expressed simply in terms of the other atoms alone. So then the atomic dynamics you can basically derive from an effective Hamiltonian, which describes some kind of input field, and also basically kind of dipole-dipole interactions between atoms. So the form of the interaction is pretty natural. It's a kind of exchange type interaction where one atom can de-excite and another atom can excite, physically mediated by a propagating photon. So in addition to these kind of coherent dynamics, you can also get dissipative dynamics, spontaneous emission. So the specific form of this kind of master equation or density matrix equation doesn't matter so much. The main thing, though, that I want to point out is that the emission term, the dissipation term, is not just an independent sum over particles, but it involves pairs of atoms. So basically involves atomic correlations. And it's that kind of correlated emission that basically encodes back the wave interference effects in radiation. Okay, so that's the kind of starting point, that one possible starting point to try and include multiple scattering and interference effects back into atom-light interactions. And I want to say that these equations are actually nothing new, so they stretch back for decades. So I think even though that these equations aren't new, I think it's fair to say that they've largely been kind of overlooked as a kind of bona fide starting point to describe atom-light interactions. And kind of one reason why is that, if you look at this problem, it looks pretty difficult, right? Because what you're trying to solve is some kind of out of equilibrium, long-range interacting, many-body dissipative spin model. So simply, 50 years ago, I don't think people really had the kind of language or toolbox to deal with that kind of problem. And so I think what we can kind of contribute now is kind of new insights. So taking ideas from other fields, like both modern photonics and also kind of condensed matter physics, we can have a totally different perspective on how we approach this problem, and also the consequences of multiple scattering. So let me now provide one simple illustration of the remarkable effects of multiple scattering and wave interference. In particular, I want to illustrate the idea that if you have an infinite 2D array of atoms, it can actually form a perfect mirror for single resonant photons coming in. So to understand this result, you basically need just kind of to understand four separate ingredients. The first is that, if I have just really isolated atoms, they don't really have any kind of internal degrees of freedom where they can just kind of eat a photon. So if I send a photon in, it can't just disappear. It has to scatter back out into some direction. The second ingredient you need to understand is that, when I have this kind of spatial order, the scattering can't really occur in random directions. So it can really only occur in kind of discrete diffraction orders, much like a kind of Bragg grating. So, one natural thing is that I can just create the fundamental diffraction orders. So if I send in light at normal instance, it can scatter back either straight back up or down. But then I can also have, for example, a first diffraction order where the atoms add a kind of in-plane momentum component to the photons. And this momentum component is going to be in units of the reciprocal lattice vector of my atomic array. The third thing to understand is that if the lattice constant d is small enough, so if it's smaller than the transition wavelength, then actually only the fundamental order is radiative. In particular, if d is too small, then this kind of in-plane wave vector, this g, actually can become bigger than the wave vector of radiating light, so bigger than omega over c. And that implies that this kind of first diffraction order can no longer radiate energy away. It's really just some kind of evanescent field. Okay. So now, as long as I have this subwavelength spacing, I send light in, and the only directions it can go are either straight back up, reflected, or transmitted. So far, everything I said here is generic to any kind of lossless dielectric element that I put in my array. And the fourth ingredient, which is really special to atoms, is that atoms have a resonance. So to illustrate the importance of this resonance, I can kind of recast this problem in the following way. So what I'm interested in is I have an array of atoms and I send in light from one direction. I can say that that problem is the equivalent to a coherent sum of two different problems, where the first problem is that I send in light from both directions and the light is in phase, plus a situation where I send in light from both directions, but then this direction here is out of phase. So now I see if I add up these two configurations, I have a plus field coming from the bottom and a minus field coming from the bottom. So that in the end says that I have no fields coming from the bottom direction. So let's consider this problem first. So because these two fields are out of phase, then in the atomic plane, the fields actually kind of cancel out. They form a node, which means that the atoms can't be driven by the field at all. And then the atoms can't, effectively don't do anything. So they're, effectively not even there. And so if I have no atoms, then basically each individual field is going to propagate past this atomic plane with a transmission coefficient of 1. If I consider the other case, now the fields constructively interfere in the plane of the atoms. But if the fields are on resonance, I argued before that generally the amplitude of the transmission coefficient has to be 1 because the photons can't disappear nor can they scatter into random directions. But then basically, on resonance, something has to happen. And it turns out what happens is that the atoms impart a pi phase shift to each of the individual plane waves. So now if I kind of add up the results, for example, if I want to calculate the transmitted field, I should take this incoming field multiplied by -1 and add to that this coming field multiplied by +1. And then I can conclude I have no total transmission on resonance. And likewise, I get 100% reflection on resonance. So this kind of 100% reflection has been observed, at least to some extent, in an experiment from Emmanuel Bloch's group last year. So this kind of special thing about the experiment is they take basically a kind of degenerate quantum gas, basically a 2D Mott insulator, to guarantee almost kind of perfect filling of the atomic array. Then they can shine in light and just kind of directly image the reflected fields. So here you really just kind of directly see the array of atoms and the high reflection. And then, if you kind of more carefully look at the spectrum of transmission reflection, they see that they can get up to basically 60% reflectance. It turns out that 60% reflectance is largely limited not by anything kind of fundamental, but more just by kind of technical issues like collection optics and so on. Okay, so the 100% reflection is a kind of neat effect, but more deeply, I think a more kind of interesting question is to ask whether that 100% reflection really signifies 100% atom-photon interaction efficiency. And so it turns out that it does, but before being too excited about that, we have to be a little bit careful, okay? Because what I showed is that an infinite 2D array acts as a 100% efficient system. But even in my kind of original textbook models based on optical depth, if I have an infinite number of atoms, it's like I have infinite resources or infinite optical depth. So even in my original models, that implies that at least in principle, I should be able to do anything I want perfectly. So to really kind of make the problem more kind of concrete, what we need to consider is finite resources. So if I have a finite atom number n, how efficient is the interaction? And so once you go to a kind of finite system, you also need to define efficiency with respect to a realistic mode, for example, some kind of Gaussian mode. So in Gaussian optical mode, I can assume that I can easily create it and collect it. So then the question you can ask is something like this. So I now have a finite atomic array, an n by n array. I say that I can efficiently create an input Gaussian fields that I can focus down to some beam waist W naught. Some of that field might get reflected and I can efficiently collect it. Maybe some of the field could get transmitted and I can efficiently collect that as well. And of course, in principle, some of the light could now scatter into 4 pi because I've broken the kind of perfect discrete translational symmetry of the system. And I have to assume that this kind of 4 pi emission I can't efficiently collect. So effectively it serves as some kind of loss of my interface. So now within this setup, you can ask, if I send in light and try to collect as much reflected light as I can, what actually is that reflection coefficient back into the same Gaussian mode? And it turns out there's 2 kinds of errors, which are quite, I think, intuitive to see. So the first error is that when you have a Gaussian beam, necessarily part of it, even if it's some exponentially small amount, has to extend beyond the boundaries of the array. So the array can't reflect that part anymore. So you can try to get rid of that effect by kind of focusing the light tighter and tighter. But then it's clear that if I focus the light so tightly that it just kind of focuses onto one atom or a few atoms, then all these kind of collective and wave interference effects have to disappear. So I won't get anything close to 100% reflection. So then it's clear that there's actually some kind of, for any finite system, there's some kind of optimal beam waist that I can choose that actually maximizes the reflection. And if you just do the analysis more carefully, what you find is that the maximum reflection you can get is 1 minus a small error, where the error goes like 1 over the n to the 4, where again, n is the linear number of atoms in the array. Okay, so that seems pretty promising that at least in principle I can get almost a perfect reflection, and then maybe I can try and interpret that as maybe almost 100% efficient atom-photon interaction. So to try and make that claim more concrete, what we can try to do now is just take that array, a finite array, and try to implement a single photon quantum memory and analyze how much error do we pick up compared to the textbook result that I presented before. And just to remind you again, what a quantum memory is, or what we'll take it to be in the following analysis, is that I'll assume it's a kind of single photon quantum memory. So I have a single photon qubit. And what I want to do is I want to reversibly map it onto some collective atomic excitation, which in principle should be long-lived. And then that would allow me to, again, map it back into a photon at a later time that I desire. Okay, so the quantum memory protocol that we'll try to implement looks something like this. So I have an atomic array. I have this kind of single photon, and I'm going to focus it onto the array with some area, with some beam area W. In terms of the level structure of the atom, this kind of single photon is going to be resonant with my G to E transition. And to make this kind of memory long-lived, what I'll assume is that there's some other atomic state R, which lives for a very long time, and that I can couple this state R to the excited state E through some kind of classical control fields. So basically, the idea of this quantum memory is that as I send in this photon, so this one photon wants to excite the system from G to E, but then I can use this kind of classical control field to basically siphon off the population from E and shelve it in this long-lived atomic state R. So one thing you might notice from this kind of cartoon is that this one photon, I've actually kind of split in two symmetrically, for example, with a beam splitter, and try to send it into the array from both directions. And you can understand that that kind of optimizes the efficiency of the quantum memory just by time reversal symmetry. So if I imagine the reverse process where I have a collective atomic excitation in an array, it's obviously going to want to emit a photon symmetrically into both directions. So then, if I want to efficiently collect, I should basically do the reverse where I send in the same photon from both directions. Okay, so once I implement this quantum memory protocol with this kind of control field, ideally what I've done is I've mapped at the end of the day, this one photon into a single atomic excitation into this kind of R level, but in a kind of superposition where this one where this one R state can be anywhere within the beam area of my incoming fields. So I won't prove it, but maybe it's kind of believable that this quantum memory has exactly the same error sources as reflection. So in particular, if I take this error and if I optimize it with respect to the beam waves, I'm again going to get an error that scales like 1 over the linear number of atoms to the 4th power. So aside from the kind of abstract scaling, we can also just kind of plot quantitatively what that error is. So that's what I've done here. On the vertical axis, I'm plotting the error, the optimized error, as a function of the linear size of the array. So that's this kind of blue curve here. And I think maybe the kind of one remarkable thing to point out is that if I just create just a small 5 by 5 array, in principle, that system can already sustain a quantum memory with an error of less than 1%. So this kind of 1 over n to the 4 scaling is also kind of remarkable because it represents a pretty strong polynomial improvement in scaling over the kind of textbook error bounds that I presented earlier. Maybe also kind of interesting is that this kind of polynomial improvement isn't really even kind of the fundamental limit. So if you change kind of geometries a little bit, so in particular, if you go to a 1D array, where the 1D array is coupled to a nanofiber, the guided nodes of a nanofiber, you can actually derive an exponential improvement where now the error is exponentially small in the optical depth of the system. So that's kind of neat. Like now that you exploit wave interference, you find that you get a huge gain for single photon applications like a quantum memory. And now, what I'd like to discuss is whether we can try to find similar gains for a broader class of applications. So in particular, instead of just linear optics, maybe the next thing we can try is to realize some kind of efficient photon-photon interaction, for example, a photon-photon gate. So if we just want to kind of directly build upon the previous ideas, what we might want to do then is just try to make this kind of mirror effect nonlinear at the single photon level. And it's not obvious that it's possible. So let me try to explain what what occurs if you just shine in light that's a little bit more intense, so something more than one photon. Imagine that I have a kind of detector, and I detect a click, so in reflection. So the fact that this array sent back one photon implies that one atom in this array had to have been excited in the first place, right? To re-emit that photon. So I don't know which atom it was fundamentally, but just for the purposes of PowerPoint illustration, let's say it's this one atom that was excited. So because it's a two-level system, this atom, which was excited, can't really respond to a second photon at the same time. It can't be excited twice. So effectively, simply the act of detecting this one photon in reflection punches a one atom hole in my mirror. So it's a bit of a nonlinear effect because this one atom hole makes the array slightly less reflecting than it was before, but it's really just a kind of small nonlinear effect. And that's because this kind of optimized beam area doesn't really just hit one atom, it hits potentially many atoms in this atomic array. So if I want to make this mirror highly nonlinear, you see that the strategy somehow has to be that detecting one photon or having one excitation punches a many atom hole in my atomic mirror. So how do we go about trying to accomplish that? So we can actually take some inspiration from ideas that are already well known in atomic ensembles. So in particular, to use the combination of electromagnetically induced transparency and Rydberg atomic interactions. So now let me kind of take a step back and explain a little bit what the concepts of EIT and Rydberg interactions actually are. And that'll give us something to compare to once we try to implement similar ideas in the atomic array. So let's go back to our kind of textbook model of a collection of atoms interacting with near resonant light. As I kind of argued before, if I send in near resonant light, each atom can rather efficiently interact or scatter the photons randomly into 4 pi. And then when I kind of get to the output, if I look in the same optical mode, that looks like a kind of absorption or loss mechanism. So particularly if I plot the transmission spectrum for weak instant light or for a single photon, on resonance, what I'll find is a transmission coefficient, transmittance, that goes like e to the minus optical depth. So instead of making my medium highly opaque to near resonant light, there's a well-known effect called electromagnetically induced transparency, where I can now make the medium transparent to resonant photons. And so to accomplish that, I'll basically kind of introduce the same auxiliary state R that I had before for the quantum memory. And again, this kind of control field that couples the state E to R. So the idea now is that if I send in a near resonant photon, which interacts with this G to E transition, then basically this kind of strong control field can again just kind of siphon away population from this kind of scattering state E into this long-lived state R. And so once I kind of suppress the population in E and this kind of random 4 pi emission of light, then what I find in the kind of transmission spectrum is a perfect, in principle, perfect transmission at one particular frequency. So EIT in itself is a pretty rich field, and I don't really have time to get into all the details. But maybe for the purposes of understanding what's to come, you basically just need to remember 2 things. So the first is that this transparency requires a resonance condition. In particular, the sum of the frequencies of the incident photon and this kind of control field has to match the frequency difference between this between the R level and the ground state G level. The second thing that one has to know is that as the photon propagates through the medium in a transparent fashion, it doesn't really remain a pure photon. So it becomes a polariton, or it strongly hybridizes with the atomic medium. And in practice, it essentially becomes almost atomic in nature. So this photon almost turns, while it's propagating inside the medium, almost turns 100% into an atomic R excitation. So EIT normally is a kind of linear optical effect. So I can send in 1 photon, 10 or 100, and these photons will be transparent in any case. But you can make this EIT effect highly nonlinear if this long-lived state R is actually a high-lying Rydberg state of the atom. And that's because when you have Rydberg, states, so so Rydberg atoms are basically atoms where the electron is really kind of loosely bound to the nucleus, so it has a kind of huge dipole moment, and that huge dipole moment causes two Rydberg atoms, which are nearby each other, to strongly interact. So in particular, if I have one atom up in my Rydberg state, then if I have another Rydberg level, if I have another atom, which is a distance d away, then the Rydberg level of this atom can potentially experience a very strong energy shift by an amount that goes like some C6 coefficient divided by distance to the sixth power. Now, what this means from the standpoint of EIT is that if I have one Rydberg excitation in my medium already, and then if D is kind of small enough, then basically I can break the EIT resonance condition. So this R level gets shifted so much in energy that my EIT can't exist anymore. And it turns out, that if you go to a high enough Rydberg level, so if the C6 coefficient is big enough, you can actually this Rydberg excitation can actually destroy the EIT resonance condition over a pretty big and even kind of macroscopically large region known as the blockade radius. So now let me just kind of explain how that kind of manifests itself in practice as a photon-photon interaction. So imagine I set up EIT conditions. I send in a first photon. So it's going to propagate in a transparent fashion and get mapped efficiently into a Rydberg excitation. And now imagine that once this first photon is inside and converted into a Rydberg excitation, I send in a second photon. So as this photon propagates through, if the second photon is far away from the first, it propagates in a transparent fashion due to EIT. But then once it enters the so-called blockade radius of the first excitation, it no longer sees EIT. It basically sees a kind of two-level medium instead. And this two-level medium is going to efficiently scatter this photon into 4 pi. So it's effectively going to be lost. So these kind of Rydberg-mediated photon-photon interactions are now routinely observed worldwide. But kind of one important thing to note is that this kind of photon-photon interaction is naturally dissipative, right? Because the first photon effectively creates a kind of a strong random scattering medium for the second photon for it to kind of disappear into 4 pi. And that essentially makes this kind of Rydberg EIT effect difficult, to some extent, to turn into a kind of coherent photon-photon interaction, like a gate. So it's possible, and but basically the kind of best known error for a gate protocol has an error that scales like 1 over the optical depth within a blockade radius to the 3/2 power. So here what we want to try is, we want to try to implement some kind of similar gate, but using the intuition that if I go to an array, this kind of two-level medium within the blockade radius is no longer dissipative, right? So because my two-level array can't scatter photons into random directions anymore. And so if I have a system where my two-level medium is fundamentally lossless, then maybe I can realize a better error scaling compared to disordered ensembles in free space. The photon-photon gate that we propose has basically 3 different steps, which I'll just explain sequentially here. So in the first step, I'll basically try to, I'll assume I have a first pulse A, which consists of either 0 or 1 photon. And I want that pulse A to conditionally change the propagation properties of a second pulse B that I'll send in later. So the first step in this gate is that I'll take this pulse A and I'll basically try to implement a quantum memory. So I'll try to store it as an atomic excitation R. And so, if this pulse A has 0 photons, then the quantum memory is pretty simple, nothing happens. So all my photons, all my atoms remain in this state G. And then if I did have a single photon in this pulse A, then basically, in the storage process, I'll efficiently map that 1 photon into a collective atomic excitation where I have 1 atom in this Rydberg state R. So once I've done this storage, the next thing I'll do is I'll take this control field and then I'll shift it away from being resonant. So I'll make it very strong and I'll make it far off resonance. And the idea of this is to essentially, try to use this detuned control field to punch a large hole in my atomic medium, centered around where the Rydberg excitation is located. So the way that it works is the following. Imagine I have one Rydberg excitation already. And then if I consider an atom that's sufficiently far away, so, for example, this atom in this corner, if I imagine that this atom was in the state E, then this atom is too far away from this Rydberg excitation to really care, to really feel any kind of Rydberg interaction in the first place. So this one atom that's far away, the effect of this kind of detuned control field is simply to implement an AC Stark shift on this level E. So this level E will get shifted in energy by amount omega squared over delta. On the other hand, if I consider a second atom, which is much closer, then basically strong Rydberg interactions will shift the R level of this atom by a huge amount. And what you see then is that this Rydberg shift is big enough that essentially destroys any kind of AC Stark shift on this level E. Okay, so an atom that's close, that's near enough to this existing Rydberg excitation sees an AC Stark shift that's ideally 0. So the picture then is basically, once I implement this kind of detuned control field, atoms far away from this Rydberg excitation and atoms nearby this Rydberg excitation will have completely different resonance frequencies on the G to E transition due to the spatially varying AC Stark shift. So the third step is then I'll send in the photon B, and this photon B will have a frequency that's compensating this AC Stark shift. Okay. So again, I have two situations. The first one is that my pulse A has 0 photons. So then all my atoms are just in the ground state. And then when I send in this photon B basically sees this kind of perfect mirror effect. So it's reflected with very high probability. On the other hand, if I stored if my pulse A had a photon and I stored it as a Rydberg excitation, then when I send in this pulse B, it effectively sees this kind of large hole in my atomic array. So then it's going to be transmitted with high probability rather than being deflected. So to understand the gate error, basically one just has to kind of believe that this gate has some kind of optimization based on the beam waste. And that's easy to see. For example, if I had no photon in A, then if I take my photon B and just kind of focus the beam waste down to just one atom or a few atoms, then obviously my reflection won't be anything close to 100%. Likewise, if I try to punch a hole in my array with some blockade radius RB, then if my photon B has a beam waste that's much bigger than the blockade radius, you see that this photon B doesn't really fit through this kind of blockade hole anymore. So it's not going to be transmitted with 100% probability. So then you see that there's a balance. The beam waste can either be too small or too big. And in particular, there should be some optimization based on the size of the blockade radius that I can achieve. So basically, the size of the blockade radius is my limiting resource. So you can optimize this gate over the beam waste as a function of the blockade radius. Not surprising, the errors that you incur are exactly the type of errors that you get in the quantum memory or even in reflection. So the error one finds is that it scales like 1 over the blockade radius to the 4th power. Okay? And aside from kind of abstract scalings, if you just do kind of realistic numerical calculations, what you find is that even for kind of moderate blockade radii, so if the blockade just covers kind of 5 lattice sites, that in principle can already bring you to an error that's less than 1%. So this kind of 1 over RB to the 4 is a pretty big polynomial improvement over the Rydberg, over the kind of known protocols in disordered ensembles. So in this error, the only thing that I've assumed is limiting is the finite size of the blockade radius itself. So of course, in a real experiment, you got any number of other kind of technical errors. So for example, the atoms could be moving. You might not get perfect filling of an atomic array. There's some question of, when you implement this Rydberg dressing, how much laser power can you actually send in, and so on. And without going into details, I do think it's reasonable to assume that each one of these kind of technical errors can be brought to kind of the 1% level. So I do believe that these types of kind of array-based gates could in principle be quite efficient. Okay, so just to kind of recap a little bit what I've discussed so far. I've tried to illustrate how by exploiting wave interference and kind of array geometries, you can get significant reduction of errors for certain applications like quantum memories and photon-photon gates. So it's a little bit provocative, but maybe it's not a crazy hypothesis to think that maybe just every application involving atoms and light can see some kind of polynomial or exponential improvement in errors if you explicitly try to exploit wave interference effects. So it's an intriguing hypothesis, and I think basically the challenge of verifying that hypothesis is that most of the other applications that one can think of involving atoms and light are many body effects. So you send in many photons and many atoms get excited. And then the challenge really comes in: how do you solve the spin model at that kind of many body level? So my group and other groups, we've been interested to try and develop techniques to deal with the spin model in that regime. And I think it's fair to say that probably we're not particularly close to understanding the full consequences of the combination of many excitations and multiple scattering of light. But from what we know, I think it's also fair to say that it seems like a pretty rich and interesting problem. And what I'd like to do in maybe just kind of 5 minutes before concluding is to try and give a little bit of the spirit of that richness of many body physics. In particular, I'll try to explain a little bit this one example here. Okay, so just to motivate a little bit the problem that we were interested in studying. It turns out that optical lattice clocks are widely viewed as a really promising next generation system for timekeeping or for frequency standard for quantum metrology. And so basically the idea of these optical lattice clocks is you first just select an atom which has some really special optical transition. So it's a high frequency transition in the optical regime. And then this transition, this kind of clock, if you want, also has a very long decay time. So the excited state can actually live for example, minutes. And the next thing you do is instead of just taking a single atom as a clock, you try to take many atoms in an optical lattice as kind of independent clocks to accumulate a high signal to noise ratio. And so at least the hope in the field is that in these kind of optical clocks, in these lattice clock systems, you might be able to get kind of fractional frequency stabilities or uncertainties on the level of 10 to the minus 18 over just kind of 1 second or a few seconds of averaging time. So to give you an idea of what that kind of represents, it means that if you could kind of take this clock and just kind of hold it in your hand, it means that you could basically resolve relativistic effects, general relativistic effects in real time as you're walking around the room. Okay, so one might ask what are the possible limitations to this lattice clock uncertainty. And I guess it's easy to believe that if you're interested in reaching 10 to the minus 18 uncertainties, then a lot of things can matter. And a lot of them are just kind of single body effects. For example, you might have kind of light shifts that, so you send in light to trap the atom, but the light kind of shifts the resonance frequency of your atoms. You might have multipolar versions of these shifts. Even black body radiation can shift the energies. And because it's single body, it means that, okay, maybe it's, at least there's some hope that you can kind of calculate and kind of quantify how big these effects are, even if the calculation itself is quite challenging and ugly. But there's other classes of effects, which, for example, are kind of many body or interaction effects. And one prominent one that we've been interested in is kind of photon-mediated dipole-dipole interactions. So it's exactly the same type of interactions that I've been trying to exploit before. So for example, you might have kind of photon-mediated coherent exchange of excitations. You might have collective emissions. So you excite some atoms and they radiate faster or slower than independent atoms. So maybe then your clock signal decays faster or slower than you expect. And I guess the point is that, in my kind of previous examples of quantum memories and so on, these kind of photon-mediated effects become strong anytime you have spatial ordering and high density of atoms. And this is exactly the same kind of situation that you would get in an optical lattice clock. So again, I think the full problem is extremely complicated. But to try and understand a little bit what might occur, what we do is we just took a kind of simple toy model where instead of considering a 3D lattice, we consider just a 1D chain of atoms, but living in 3-dimensional space and undergoing dipole-dipole reactions. So how would this kind of simple system function as an optical lattice clock? And the choice of this geometry is pretty simple. Basically, if you restrict yourself to 1D, then you can actually kind of in numerics reach the kind of many-body limit without being overwhelmed by finite size or boundary effects. So the first thing you can do before studying kind of an actual clock is just to understand what happens in for a single excitation. So then if you diagonalize the effect of non-Hermitian Hamiltonian for this system, then because of the translational symmetry, your eigenstates will be pretty close to spin waves, where each atom is excited with some phase k. And then I guess one special thing that occurs is that when your lattice constant is small enough, so basically sub-wavelength, then your spin wave vector, which can be as large as pi over d, that's just the kind of size of the Brillouin zone, that can actually be larger than, again, the wave vector of radiation fields, omega over c. So what that means is that some of these spin waves can actually decouple from radiation fields, and therefore that this excitation should be long-lived. And there's actually some nice intuition. So these are basically just these kind of special states where the k vector is too big. For those states, basically this atomic array functions as a kind of fancy optical waveguide. So basically this excitation isn't allowed to emit into free space along the bulk. It can really only emit energy at the boundaries where the translational symmetry of the system is broken. And because the emission, the spontaneous emission can only occur at the boundaries, what you find is that, for a finite size system, the system can be actually highly subradiant. So there's some eigenstates where the spontaneous emission rate scales like 1 over the number of atoms cubed times alpha squared, where alpha is just an index for the subradiant modes. So alpha equals 1 is the most subradiant mode, alpha equals 2 is the second most subradiant mode, and so on. So now the richness comes already when you consider the two-excitation manifold. So if you believe that this chain of atoms acts as a kind of optical waveguide, then you can imagine that I can first create one optically waveguided excitation. But because my atoms are two-level, it means that this waveguided excitation somewhere along this wave packet, it creates a kind of atomic excitation. So this one atom which is excited can't be excited a second time. So then what happens if I try to create a second wave-guided excitation is that the second photon effectively sees this one excited atom as a defect or a hole in the waveguide. So it can basically scatter off that hole into free space. So this basically, this 1D chain is like a kind of exotic waveguide where it can't guide overlapping photons. So now if I want to kind of guide two photons or create kind of subradiant states of two excitations, then the strategy is somehow I should kind of enforce some kind of spatial repulsion of these photons. So for example, like a Pauli exclusion principle. And it turns out you can make that argument really more precise. So basically, if you want to create a waveguided or highly subradiant two-excitation state, what you should do kind of symbolically is define kind of fermionic-like spin wave operators. And so the first thing you do is you create one excitation in the single excitation state, which is subradiant. By kind of fermionic statistics, you can't populate this state twice. But then what you can do is you can populate the second most subradiant mode with a single excitation. So the decay structure of that two excitation subradiant state looks a little bit like this. So basically what happens is that these two excitations kind of decay as their individual elements do. So in particular, this kind of, if I create a two excitation state, which is a combination of the first and second most subradiant states or modes, then the second most subradiant mode is more likely to decay first, which means that this two excitation state is more likely to decay into into a single excitation, which is the most subradiant state of the system. And it turns out you can kind of generalize that argument to even higher excitations. Basically, the idea is that if you start from some highly excited state, then as it kind of decays down, the system will become progressively more subradiant. So the remaining excitations will last longer and longer inside the system. And so you can, in this 1D system, you can just do kind of numerics. So for example, you can consider any kind of highly excited state, like a completely inverted state. And then you can plot as a function of time, the total number of excitations remaining in the system. And you see that as you get to kind of sufficiently large system sizes, so kind of some thermodynamic limit, the decay rate of the remaining excitations really slows down at long times. And in fact, it even diverges from an exponential. So at long times, it turns into a kind of power law decay. So what that suggests is that your atoms in the array are nothing like independent oscillators. And furthermore, if you look at kind of long times, you can see, if you can measure which atoms are excited, then what you see is at long times is this kind of dynamic buildup of fermionic correlations between the remaining excitations in the system. So again, this discussion was meant to just give you a flavor of, the possible richness that comes in the combination of multiple scattering or dipole-dipole interactions and many-body physics. So I don't really have time to really explain, what are the kind of potential consequences for an actual lattice clock. I'll just simply refer you to this paper here. But hopefully it convinces you that, an actual lattice clock could potentially be a rich many-body problem. And so with that, I'm done. And I guess my kind of final message is that, in these kind of atom-like interfaces, if you can exploit multiple scattering and wave interference, I think this really opens up a lot of potentially rich physics and exciting technological applications. So thanks.